Well, hello everyone. You know today is going to be a great day because you get to learn more about chemistry. So in this lesson, we are going to be discussing a little bit more about stoichiometry principles and how they can be applied in order to determine things like atom economy as well as the empirical formula of hydrates. So this is kind of like a catch-all video. Other stoichiometry principles you need to know for IB chemistry, but don't really have their own category. So bear with me because this one's a little bit disjointed. So as a review, we're going to talk about theoretical versus actual yield. So whenever we try to determine the amount of product made from a reaction, that is called the theoretical yield. It's the maximum amount of product that can be formed from a given amount of reactants. However, it is not the same as actual yield, which is when you are doing the experiment in the laboratory and you actually measure the amount of product you made. So for example, what if the theoretical yield you're supposed to get was, I don't know what this is, it looks like 42-ish mils of something, and you actually get about 24. So that's not a very good yield. But you can measure how efficient your experiment is by using something called the percent yield. So it's a measure of how successful your reaction is by measuring the expression or the ratio between the actual yield and the theoretical yield. And this is expressed as a percent. So for example, if the actual yield of water in the first problem was 25, the percent yield of the reaction would be 25 divided by, I don't know, 42-ish times 100. So I'm not really sure what that would be, but it's probably going to be a little bit over 50% if I can do mental math in my head, right? Which, maybe sometimes I can, sometimes I can't, but let's just do 25. Yeah, that's about actually 60%. So you got about a 60% yield. So based on that, you can identify perhaps areas of systematic and random error and then modify your procedure accordingly in order to improve your percent yield. So in an industrial setting, even if a reaction has 100% yield, it may not be efficient in another sense. For example, using a principle called atom economy. So atom economy is basically measuring how much of a product of interest you are making in a reaction because many reactions produce byproducts that are not of use. So the atom economy is going to be the measure of the mass of the useful products compared to the mass of the reactants. It's not the same as percent yield. It's basically telling you how much of the product you wanted to make from the reaction did you actually make. So for example, if you are doing an industrial reaction where you are producing hydrogen chloride gas in order to, make hydrochloric acid, you have to react salt and sulfuric acid, and then that makes hydrogen chloride gas. It's not an acid unless it is dissolved in water and it's aqueous. So this is your useful product, but it also produces sodium sulfate as a byproduct. So what you're going to do is take the molecular mass of your hydrogen chloride gas and taking into account the stoichiometry, so multiply it by 2, divided by the total molecular mass of the reactants, again taking their stoichiometric coefficients into consideration, and then multiplying it by 100. The molar mass of the product, multiplying it by 2, of course, is 72.92 grams per mole, whereas the molar mass of the reactants, added all together and multiplying the sodium chloride by 2, would be 214.96 grams per mole. So, therefore, if you divide that number, you get 72.92 divided by 214.96. Let's do this in my calculator really quick, on my phone calculator, because I don't have my other one handy. That's only a 33.9%. So when you're doing the reaction, only 33.9% of your reactants will turn into useful products. So quite a large portion of your reaction will be substances that aren't of interest to you, in this case, sodium sulfate. So in order to get around this, you can either use a different type of reaction, or maybe you can utilize those byproducts for something else. But this kind of tells you, economically speaking, how efficient your reaction will be. Okay, so here is it written out. 2 multiplied by the molar mass of the product of interest, which is the hydrogen chloride gas, divided by the molar mass of the reactants, taking into account 2 sodium chlorides. So again, 33.92% as the atom economy. So you guys can try an example problem. You can calculate the atom economy for this reaction. So this is a different reaction to produce hydrogen chloride gas. And so based on that, which reaction do you think is more efficient in an industrial setting? So if we wanted to produce sodium chloride, for example, through the reaction of sodium hydrogen carbonate with hydrochloric acid, or the reaction of sodium hydroxide with hydrochloric acid, which one would be most efficient in terms of the atom economy? So looking at the first equation, I could already probably tell the second one is going to be more efficient, not only because it produces less byproducts, but the molar mass of the reactants is overall smaller in the second equation compared to the first one. So that means a smaller denominator and therefore a larger percentage will be achieved in this second reaction here. And also just thinking about environmentally speaking, like you're not producing carbon dioxide gas in the second equation. So it's probably better overall. Here's another practice problem where you can extract iron from its ore using the following reaction. You add carbon monoxide gas to iron 3 oxide to produce carbon dioxide gas and iron. So this type of reaction is actually a redox reaction to extract the iron from the iron oxide. So you can calculate the atom economy by dividing the molar mass of the iron by the molar mass of the reactants. Of course, don't forget to multiply the carbon monoxide by 3. Okay, moving on to the last part of this presentation, we're going to be talking about hydrate. So we're kind of deviating from percent yield and atom economy and now talking about hydrates. This again will utilize stoichiometry principles just in a different way. So hydrates occur when some ionic solids crystallize from an aqueous solution, so the water is incorporated into their crystal structure. The water however, is not randomly distributed, but is incorporated in an orderly arrangement in a fixed ratio within the salt. So for example, if we zoom in on this salt, you can see the water molecules are incorporated in a fixed pattern within this ionic solid. So salts that contain water in this manner are called hydrates, and they are represented by a different type of formula than just the ionic compound. And we'll talk about that in just a second. I just wanted to show you 3-dimensionally. This is an example of a hydrate, and you can see all the water molecules orderly arranged within this crystal lattice. Okay, so naming hydrates. It all depends on how many water molecules are incorporated per formula unit of the ionic solid. And remember, a formula unit is the smallest unit of an ionic compound. You can't call the smallest unit of an ionic compound a molecule like you can with a covalent compound because they are ionic bonds, not covalent. So you call them formula units. So for example, if you have copper 2 chloride, it incorporates 2 waters for every 1 copper chloride formula unit. So every 1 CuCl2 unit, there are going to be 2 waters. So we can represent that by using the formula for copper 2 chloride, putting a dot after it on the formula, and then listing how many waters are in every formula unit. So, and you also want to name the hydrate using a Greek prefix to indicate the number of waters per formula unit of salt. So for example, if there are going to be 2 waters incorporated in the hydrate, it is called copper 2 chloride dihydrate. And then again, you separate the waters from the ionic salt using a dot and then including the number of water molecules. So here's how it would look: copper chloride dihydrate. So you have this dot here and then the number of water molecules within each formula unit. Okay, so the opposite of a hydrate is called an anhydrate. When you heat up a hydrate, of course, you are allowing the water to evaporate, and then it loses its water and it's called an anhydrate. So, for example, if you were to heat up copper sulfate pentahydrate, and remember we call it that because of the 5 water molecules per formula unit of copper sulfate, then you can see how the ionic solid changes without that water incorporated into its structure. So, of course, it's going to have a lot lower molar mass without that water incorporated. Weighing the hydrate before and after heating can actually be used to determine that stoichiometric coefficient in front of the water. So you can figure out the ratio of water to formula units in the hydrate by doing this very simple lab procedure. So again, you can see the hydrate versus the anhydrate, how their ionic solids are different. You can also see that after the water is removed, the color changes. So copper sulfate pentahydrate is a bright blue color. It's the color most commonly associated with copper sulfate. But after you remove the water, it turns to this grayish color. And that's because whenever you have water complexing with the copper sulfate, the d orbitals are actually split because of the water ligands, which causes the electrons in those split sublevels to absorb energy. And when that happens, we see a complementary color to the wavelength of light that is absorbed. So in this case with copper sulfate, we see a blue color, but without the water, we don't have that splitting of the d sublevels, and therefore we don't have the movement of d electrons between those sublevels to cause that visible blue color. Okay, again, hydrate versus anhydrate. You can see the same thing happens for like copper 2 chloride. So copper 2 chloride is a lovely green color, but when the water is removed, it kind of looks like just dirt. Okay, so on to the best part. How do we actually do this practical procedure to determine the empirical formula of a hydrate? So it's very simple. What you want to do is take a flask with your hydrate. So in this case, it will be magnesium sulfate hydrate, but we don't know the number of water molecules in each formula unit. And you want to heat it up until all the water is released. So if the flask by itself weighed 117 grams, and then the flask and the hydrate had a mass of 126.8 grams, you can then figure out the mass of the hydrate in that flask by just subtracting the two numbers. Then you would heat your hydrate until all of the water was released. And you usually want to do several steps where you heat it, let it cool down, weigh it, heat it, let it cool down, and weigh it. And you want to make sure there's no change between each round of heating. That way you know you have fully released all of the water molecules. And you also don't want to weigh it when it's hot because that can definitely affect your reading of the mass. So after it is completely heated and all the water is removed, you can measure the flask plus the anhydrate to be 121.8 grams. So when you're doing a problem like this, you first want to find the mass of both the water released as well as the original hydrate that you are experimenting with. So you're going to subtract the final mass after the water is removed from the mass of the flask plus the hydrate in order to get the mass of water released, which was 5 grams. Then I am going to divide by the molar mass of water in order to get the moles of water released. Then what I'm going to do is do the same thing, but with the mass of the hydrate. So I'm going to subtract the mass of the flask with the hydrate minus the flask to get just the mass of the hydrate, which in this case was 9.8 grams. Then I'm going to divide the mass of the hydrate by the molar mass in order to find the moles of hydrate. Then, because the empirical formula of a hydrate is going to be how many waters are in each formula unit, so if I divide those two moles, I can determine the stoichiometric coefficient of the water, or the ratio of water per mole of hydrate. So I divided the two mole values I got in order to get about 3.4, which we can round to approximately 3. So the stoichiometric coefficients of hydrates are always whole numbers. And when you're doing this experimentally, sometimes it's a little bit tricky to determine what the coefficient is. But in this case, it is 3 because magnesium sulfate trihydrate is a very common hydrate of this salt. So sometimes you have to do a little bit of research to look at the common hydrates that do form for these ionic compounds. All right, guys, that is it for this video. Please let me know if you have any questions, and I hope you have a great day. Bye.